Recall the lemma that relates the number of misses in an LRU cache to the number in one with optimal replacement. From this lemma, there's a corollary about regularity. You can design an algorithm for an ideal cache, and if that analysis shows that the number of misses is regular, then an LRU cache will perform just as well. So let's see how to use this. Suppose you design a matrix multiply algorithm assuming a conventional non-Strassen scheme, and you do so for an ideal cache. Let's say that your analysis shows your algorithm does n cubed over L root z misses. For this example, let's further assume that the line size is one word. So, will this algorithm perform well on a machine with an LRU cache? Let's check the regularity condition. What happens when you double the cache size? Well, it introduces just a small constant factor. So, the regularity condition is satisfied. And because QOPT is regular, QLRU will be proportional to it. By the lemma, you could also evaluate the right-hand side of this relation. Here's what you get. Basically, an upper bound on the number of LRU misses. This brings us to one of life's great pleasures. Well, assuming you're a bit of a geek. Or is it nerd? Let's just say enthusiast, shall we? The pleasure is that the lemma is not hard to see. For simplicity, let's assume that the transfer size is one word. Now imagine the sequence or trace of all load and store operations performed by a program. Divide this trace into phases. Let's define these phases in a special way. In particular, suppose that each phase references exactly z unique addresses. Just to be clear, each phase might contain many more than z loads and stores. The phases might also have widely varying numbers of loads and stores, as the illustration suggests. But the number of unique addresses is always exactly z in each phase. Now, let's say the machine has an LRU cache of size z. Think about what happens during some phase, let's say phase I. At the beginning of the phase, it's possible that the cache is full. So, the first time each unique address of phase I is seen, it could cause an eviction. Thus, by the definition of a phase, the number of cache misses could be as high as z. Now think about what happens on a cache with optimal replacement, but half the capacity, z over 2. Remember, this optimal cache can gaze into its crystal ball to see all future accesses. So, during the previous phase, I-1, what might the optimal replacement policy have done? Well, it may have arranged itself so that the first z over 2 unique addresses seen in phase I are exactly in cache. That would mean no evictions. But since the optimal cache is only of size z over 2, then it must at that point start loading addresses. In other words, the smaller but all-seeing cache has to perform at least z over 2 transfers. The competitiveness lemma then follows from these two facts. One is at most z, and twice the other is at least z.